Imagine falling towards the ultimate cosmic enigma, a black hole. Its gravity is so intense, not even light can escape once it crosses a certain boundary. What would actually happen to you? First, you'd feel a pull, unlike anything experienced before. As you get closer, the force strengthens exponentially. There's no turning back. No rocket, no speed can overcome this gravitational embrace. This point of no return is called the event horizon. Crossing it means saying goodbye to the observable universe forever. From there, all paths lead inward, towards the singularity. Before you reach the singularity, another terrifying phenomenon awaits: spaghettification. The intense tidal forces stretch your body like pasta, longer and thinner, while compressing it horizontally. Your feet, being closer to the black hole, would feel a much stronger gravitational pull than your head. This difference in force, not the absolute gravity, is what causes the horrific stretching. Eventually, every molecule in your body would be ripped apart, pulled into an infinitely thin strand. Your existence as a coherent entity would cease, long before reaching the very center. From an external observer's perspective, watching you fall would be stranger still. You'd appear to slow down, getting redder and dimmer, eventually freezing at the event horizon. This perceived slowing is due to extreme time dilation. As gravity warps space-time, time passes differently for you near the black hole than for observers far away. Your clock would simply tick slower. The redness comes from gravitational redshift. Light waves emitted from near the black hole lose energy as they climb out of the gravity well, shifting to longer, redder wavelengths. For you, the fall past the event horizon would be incredibly swift. You wouldn't perceive the freezing or fading seen by others. It would be a rapid, unyielding journey to annihilation. At the very heart of a black hole lies the singularity, a point of infinite density where all the mass is crushed into zero volume. Here, our current laws of physics break down entirely. Understanding the singularity requires a theory of quantum gravity, reconciling general relativity with quantum mechanics. This remains one of the greatest unsolved puzzles in theoretical physics. Not all black holes are formed from collapsed stars. Some, called primordial black holes, might have formed in the early universe, just moments after the Big Bang, enduring to this day. Stellar mass black holes are born from the catastrophic collapse of massive stars at the end of their lives. These are typically a few to tens of times the mass of our Sun. Then there are supermassive black holes, millions to billions of times the Sun's mass. They reside at the centers of most galaxies, including our own Milky Way, influencing galactic evolution. Our Milky Way's supermassive black hole is Sagittarius A. It's about 4 million times the mass of the Sun, quietly anchoring our galaxy's spinning arms. When two black holes collide, they can merge into an even larger one, releasing incredibly powerful gravitational waves that ripple through space-time, recently detected by LIGO. The detection of gravitational waves confirmed a major prediction of Einstein's theory of general relativity. It opened a new window into observing the universe beyond electromagnetic radiation. Supermassive black holes sometimes actively feed, pulling in vast amounts of gas and dust. This creates incredibly luminous active galactic nuclei, AGN, outshining entire galaxies. Quasars and blazars are types of AGN, distinguished by the angle at which we view their powerful jets. They are among the brightest objects in the distant universe, crucial for cosmology. Stellar black holes form when a massive star exhausts its nuclear fuel. Without the outward pressure from fusion, the star's core collapses under its own immense gravity. For a star to collapse into a black hole, its core must exceed a certain mass, known as the Chandrasekhar limit. Below this, it might become a white dwarf or neutron star. The size of the black hole dictates your fate. For a supermassive black hole, the event horizon is so vast that tidal forces are less extreme, at least initially. You might cross it intact. If falling into a supermassive black hole, your initial experience might be eerily normal. You wouldn't immediately feel the stretching. The horizon would simply be a featureless boundary. However, the view of the universe behind you would become increasingly distorted. Light from distant stars and galaxies would be bent and warped, eventually compressing into a tiny, brilliant point. Once past the event horizon, even light cannot travel outwards. Every direction points towards the singularity. There's no possible trajectory that leads back to safety. For rotating black holes, there might even be an inner event horizon. What lies beyond is speculative, possibly leading to a different region of spacetime or even another universe. Black holes act as powerful gravitational lenses, bending the light of objects behind them. This can create distorted, multiple images, or even Einstein rings of background galaxies. Black holes aren't entirely black. Stephen Hawking theorized they emit Hawking radiation due to quantum effects near the event horizon, slowly causing them to evaporate. This evaporation is incredibly slow for large black holes, taking trillions of years. But for tiny primordial black holes, it could happen quickly, ending in a burst of gamma rays. Hawking radiation poses the information paradox. If black holes evaporate, what happens to the information about everything that fell in? Is it truly lost, violating quantum mechanics? One proposed solution is the holographic principle, suggesting that information isn't lost but encoded on the black hole's event horizon, like a cosmic hologram. Another theory, fuzzballs, proposes that black holes aren't singularities but dense, string theory objects. This could avoid the information loss problem and the singularity itself. Despite their immense gravity, black holes don't suck things in like cosmic vacuum cleaners. You only fall in if you cross the event horizon, meaning you pass too close to them. Objects can orbit black holes for billions of years, just like Earth orbits the Sun. Our solar system isn't in danger of falling into Sagittarius A anytime soon. How do we even detect something that doesn't emit light? Scientists observe black holes through their effects on surrounding matter and the gravitational waves they produce. The most visible evidence comes from accretion disks. Gas and dust spiral into black holes, heating up to extreme temperatures and emitting incredible amounts of X-rays and gamma rays. Ongoing research aims to further test Einstein's theories in extreme gravitational environments, exploring the nature of spacetime itself and the fundamental laws of the universe. The no-hair theorem states that a black hole is fully characterized by only three properties: its mass, charge, and angular momentum. Everything else is hair that's lost. Black holes also have a life cycle, albeit an extremely long one. They grow by consuming matter and merging with other black holes, eventually slowly evaporating through Hawking radiation. The birth of some black holes is marked by incredibly powerful gamma-ray bursts, the most energetic explosions in the universe, visible across billions of light years. Between stellar and supermassive, there's a hunt for intermediate mass black holes. These are elusive, potentially forming in dense star clusters, bridging the size gap. Theoretically, some black hole solutions to Einstein's equations suggest wormholes, shortcuts through space-time. Could they be traversable, leading to distant regions or times? Unfortunately, traversable wormholes would require exotic matter with negative energy density to stabilize them, something we haven't found and may not even exist. The firewall paradox is another puzzle, suggesting a blazing hot firewall at the event horizon, instantly incinerating anything that crosses it. This contradicts a smooth entry. The firewall paradox arises from trying to reconcile quantum entanglement with smooth entry and Hawking radiation. It shows how deeply intertwined these fundamental concepts are. The Event Horizon Telescope provided the first ever image of a black hole's shadow, a dark core surrounded by a bright ring of light, confirming theoretical predictions with stunning accuracy. The monumental image was of M87 star, a supermassive black hole at the center of the M87 galaxy, billions of times the mass of our Sun, a triumph of international collaboration. Future upgrades to the EHT will allow for clearer, even real-time imaging of black holes, potentially revealing more about the dynamics of accretion disks and jet formation. Black holes represent the most extreme endpoints of cosmic evolution. They are fundamental to galaxy formation, regulating the growth of stars and the distribution of matter. They are also natural laboratories for studying conditions we can never recreate on Earth: extreme gravity, warped spacetime, and the limits of our understanding of physics. While they destroy matter, black holes also play a role in cosmic recycling. The energy released from their accretion disks can heat and disperse gas, preventing star formation in some regions. Black holes are a profound testament to Albert Einstein's genius. His equations predicted their existence long before we had any observational evidence, spanning decades of scientific pursuit. Despite incredible progress, many questions remain. What is the true nature of the singularity? Can information truly be preserved? What lies beyond the event horizon? These cosmic enigmas continually push the boundaries of human knowledge, forcing us to invent new physics and imagine new realities far beyond our intuitive grasp. So, falling into a black hole would be a journey into ultimate oblivion, a dramatic dance with gravity ending in spaghettification and molecular disintegration, a truly one-way trip. The universe is full of these gravitational monsters. Their study not only satisfies our curiosity, but also helps us understand the very fabric of our reality, space, and time. The mere thought of such a cosmic fall ignites our imagination, forcing us to confront the immense power of nature and the humility of our place within the vastness of space. While a human journey into a black hole remains science fiction, our journey of knowledge into their mysteries continues, layer by fascinating layer, broadening our cosmic perspective. What are your thoughts on black holes and the fate of those who might venture too close? Share your theories and questions in the comments below. If you're fascinated by the universe's most extreme phenomena, remember to like this video and subscribe for more deep dives into space science.